You know, when you think about the world's most advanced aircraft, you probably think about stealth, engines, or weapons. But today, we're going to talk about the unsung hero, the digital nervous system that makes it all work. It's a piece of tech from the 1970s that's, believe it or not, still flying high. I'm talking about MIL-STD-1553B. Now, that might just sound like a bunch of letters and numbers, but trust me, its story is an absolute masterclass in brilliant, lasting design.
So how did this thing become so important? Well, here's what we're going to do. First, we'll look at the absolute mess it replaced. Then, we'll dive into its super smart solution, this data highway, and figure out how it all works. We'll also see what key upgrade made it a game changer, and finally, we'll ask why this tech from decades ago is still so crucial today.
Okay, so let's jump in a time machine. Before 1553 came along, if you could peel back the skin of a complex military jet, well, you wouldn't find anything clean or organized. You'd just find pure, unadulterated chaos.
Just try to picture it. Every single time you wanted to add a new system, say a new sensor or a new cockpit display, you had to run a whole new set of dedicated wires to every single other thing it needed to communicate with. It created this literal rat's nest of copper wiring. And that's not just ugly, right? It was incredibly heavy, and every single one of those connections was a new point of failure just waiting to break at the worst possible moment.
So, out of that total mess came an idea that was, frankly, revolutionary. This is where MIL-STD-1553 shows up and completely changes the game.
And the core idea? It was beautiful in its simplicity. Instead of that spider web of wires, 1553 introduced a single shared communication channel. A data bus. The data highway analogy is just perfect. Think about it. They basically replaced thousands of tiny, winding private roads with one clean, efficient superhighway that every system could use to talk to every other system.
Okay, so you've got this superhighway, but how do you stop all the data from crashing into each other? Well, it all comes down to having some really strict rules of the road and a few very clearly defined roles for everyone on the bus.
First up, and most important, is the bus controller, or BC. This is the maestro of the whole orchestra, the big boss. It has absolute, total authority. Seriously, nothing happens on this data bus unless the bus controller says so. No message gets sent, no data moves until the BC gives the command. It's the one and only traffic cop for the entire network.
Then you've got the remote terminals, the RTs. These are all the other devices on the plane. You know, the radar, the flight controls, the weapons systems. If the bus controller is the conductor, then the RTs are the musicians. Each one is a virtuoso on its instrument, totally ready to go, but they stay completely silent. They do not speak unless spoken to by the maestro.
And there's a third role, which is actually pretty cool, the bus monitor. Now, this thing is like a silent spy on the network. Most of the time, it just listens in on all the conversations, kind of like a black box flight recorder, just logging everything for later analysis. But, and this is the really clever bit, it's also a backup. If the main bus controller ever fails, the bus monitor can step in and take over instantly. It's redundancy, built right into the system.
So the whole thing works in this really simple, really solid loop. The bus controller sends a command to a specific remote terminal. The RT gets it and immediately sends back a little message called a status word, which basically says, "Yep, I got your message and I'm good to go." Then, if asked, it sends the data. That's it. It's this super predictable command and response rhythm that makes sure there's absolutely no chaos on the bus.
So, how fast is this data highway? 1 megabit per second. I know, that sounds painfully slow, right? I mean, your phone is probably downloading hundreds of times faster than that right now. But here's the thing, and this is so important, speed was never the point. The goal wasn't to be fast. The goal was to be absolutely positively 100% reliable. And for that, it was a work of genius.
And a huge part of that reliability is something called Manchester second encoding. Now, this is a bit techy, but the basic idea is amazing. Every single bit of data, every 1 and every 0, has a change in voltage right in the middle of it. So what does that do? It means the timing, the clock signal, is baked right into the data itself. It's self-clocking. And that makes it unbelievably tough and resistant to all the electrical noise and interference you'd expect to find buzzing around inside a military aircraft. Now, the standard wasn't perfect right out of the gate. The first version, 1553A, was a great start, a huge leap forward for sure. But it had one big critical flaw. And fixing that problem is what gave us the B version, the version that became the legend we're still using today.
So what was the problem with 1553A? Well, it left too many things open to interpretation. It had all these options that a designer could choose to use, or not. And the result was a total mess, a kind of digital Tower of Babel, where hardware from one company couldn't talk to hardware from another. 1553B came in and fixed that. It got rid of the ambiguity, it standardized all those options, and by doing that it created a true interchangeable plug-and-play system where everyone was finally speaking the exact same language.
The B version didn't just fix things, it added some really powerful new features. It introduced special mode codes that let the bus controller manage the network better. It officially defined that awesome backup bus monitor role we mentioned. And it added a broadcast option. This is a really big deal. It meant the bus controller could now send a single message, like a critical safety warning, to every single device on the bus at the exact same time. Super powerful and super efficient.
Which brings us back to the big question. Why on earth are we still talking about a standard that's almost half a century old? And the answer couldn't be simpler. Because it just works. And it doesn't just work, it works unbelievably well.
Get a load of this number. The standard is so robust, you can expect an undetected data error only once in every trillion bits. A trillion. It's hard to even wrap your head around that. To put it another way, that's like having a single typo in a stack of books that's over 400 miles high. That is the kind of rock-solid reliability you can literally bet your life on. And for pilots, that's exactly what they're doing every single day. And that is why, ever since 1553B was released back in 1978, it became the digital backbone for some of the most iconic aircraft in history. We're talking the F-16, the F-18, the Apache helicopter. It's even been used on the International Space Station. For more than 50 years, this thing has just proven itself over and over again.
So, it all leaves you with this one big question. In our world, where we're just obsessed with speed and the next new thing, MIL Standard 1553B stands as this monument to the power of simplicity and, above all, reliability. It's proof that sometimes the best technology isn't the fastest or the shiniest, it's the one you can trust with your life. And it really makes you wonder. After being the undisputed king of aerospace for half a century, what in the world could ever replace a legend like this?